So this is the last example that we did last time. We wanted to get the scalar equation of the plane. It's the same as just saying we want to get the equation of the plane, and we got the vector, the distance vector from P to Q, and we also got the one from P to R. Then when we have our PQ and our PR, we got their cross product to get the normal force. Yeah, so the normal force helped us to get the values that were necessary for us to have. That's your A. So the N, the normal vector, gives you your A, so that we can do A multiplying X minus X naught using the first point. That's the last thing that we did last time. Yeah, so we got something that looks like this. Is Y minus 2. So you can use any point here because they're all on the same plane. Yeah, but we mostly just prefer the first one. Yeah, it fits the X naught description very well. So yeah. Then apart from this, the second, let me just remind you using this example here. They are saying we need to find the vector equation containing the line which is perpendicular to this, to the other line here. So we have L1 and we have L2. So the first thing that we do is to try to see, to try to get the normal vector rather. The direction vectors are already given. We're having this guy and we're having this. So we'll get the cross product. That's going to be, let me write it here. So L1 is given as X, Y, Z. There's 1, 2, 4. And there's plus a T. This is 4, 1 and M. Then L2 is X, Y, Z. This is equal to, there's a 4, there's a 15, and there's 8. Yeah, there's M. We have 2, 3, and negative 1. Yeah, so since these are already the direction vectors given, it's like your PQ and your PR. Yeah, so we're going to get the normal vectors, the normal vector by getting their cross product. Yeah, so this is just going to be IJ and K. The first one is going to be on top here. That's a 4, 1 for the first line. The second one, you have this. When you're done solving this, because this is going to be I, the determinant of this part, minus J, 4, 2, 11, and negative 1, plus a K, you have 4, 1, 2, 3. Then from here, we can just get our N. Our N is giving us negative 34, 26, and a 10. So you pick any of the points because it's like these were just points on the plane. Yeah, this point or that point. You can pick either. Yeah, so if you pick the first one, meaning the equation of the plane is just going to be a negative 34. Then you have X minus 1. Then you have 26, which is Y minus the 2. Then you have Z, which is equal to 10 minus 10, Z minus a 4. Yeah, we equate this to 0. So when you simplify this whole thing, it will give you the equation of the plane. Yeah, so that's basically what we needed to do, and the simplified version is going to give you something like this. If you finish it off, there's a 17x minus 13y minus 5z plus a 29 is equal to a 0. Yeah, this is what you should get. So that's the last thing that we were doing in our physical session that we had. Now I want to finish it off by looking at there are 5 things I think that we need to talk about. The intersection of a line and a plane. So if you want to check the intersection of a line and a plane, I'll go straight to an example. These are the cases that you can have. You can see here you can have a line and a plane intersect at a point, just at a point, meaning it's like giving us a one solution because the line is piercing the plane, sort of just touching the plane at one particular point. Yeah, then here we have the line lies on the plane, meaning they are meeting at so many points. Yeah, infinite number of solutions. Then we can have a line and a plane that do not intersect, but they could be parallel, so you have something like that. Yeah, so let's look at these examples here. Yeah, so they're saying determine whether the following pairs of lines and planes intersect or not. Yeah, so the first one, we just have to parameterize the line. Yeah, we need to write it back into its normal form. So we take it back into having x is equal to, that's the same as 2t plus 5. I'm just taking this guy back. And also we have y, which is equal to negative 5t minus 5. Right? If you multiply this by t, then take the 5 on the other side. Then our z is equal to 3t plus 2. So we need the parametric expressions for the line. Then we replace them in the original equation for the plane. So we equate where there's x, we'll put this guy. Where there's y, we'll put this. Where there's z, in the equation for the plane. Yeah. So if we were to do that, so here we're doing intersection of a line and a plane. Yeah, so the equation of the plane was given to be 9x plus 13y minus 2z is equal to 29. If we try to replace with the parameterized components of the line into the plane, that's going to be a 9. Where there's x, we're going to put a 2t plus a 5. Where there is y, we're going to say negative 5t minus 5 minus 2. Where there's z, we're going to say 3t plus 2 equal to 0. So when we solve this whole expression, like when you just expand everything, yeah, it's going to give you something that's very straightforward. You're going to end up by getting 53t, which is equal to a 53, meaning t is equal to negative 1 when you're done solving. So if there's a solution, it means the plane and the line intersect at some point. And to get that particular point, we can just replace the t into the values of the parametric expressions of the line that we had. Remember we said x is equal to what? X is equal to 2t then plus 5, right? So meaning the point where they're intersecting could be x is equal to, put the negative 1 there, that's going to give us a 3. Then the y component, again, you can get it. That's a negative 5t minus 5. Put the 1 there, that's going to give us a positive. That's a 0. Z, on the other hand, gives us 3t plus 2, meaning z is equal to negative 1. So this is the point where they are intersecting in 3D. Yeah, this is what we get. Once you're able to get the t value, like the expression you get is solvable, it means they intersect. Yeah. So for part B, I'll just give you a guide to lessen the time. Part B, it's already parameterized, this guy here, right? So put wherever there's x, put this. Wherever there's y, put this guy. Wherever there's z, put this. You'll notice that all the t values expression are going to cancel when you try to solve it. There is no solution for t, meaning they do not intersect. Yeah, so hence no intersection. That's how you just identify it. Yeah, so try this, just confirm what I'm saying. The same applies to the last one. This is already like this, so x is equal to what? Negative 2 plus 3t. Then your y is equal to what? 4 plus t. Then you have your z is equal to 1 minus t. Again, do the same for part C. So if you put this expression, these guys here, if you put them, substitute them into the plane and try to simplify, you're going to notice that the left and the right here, there's no solution because the numbers you're going to get are totally different. You're going to have there are numbers which is not going to make sense. You get something like on the left you say negative 21 is equal to 10, so there's no intersection. So even here the lines are going to have a no intersections, but this is going to be what? This is going to be, can we try this? Can we try to solve it? Let's see if the t cancels. We get what? When you replace where there is x, let's try to get it. Where there's x, put negative this. Where there's y, put 4 plus t. Where there's z, put 1 minus t. Equate this to 0. This is 12t minus 4 minus t plus 11 minus 11t is equal to 0. And this is equal to, so 12t 11. So if we try to say this is going to be what? This is going to give us this is what? This is 12 minus 1, that's 11. So the t goes away. Then we have negative 8. The whole expression for part C. Oh, there was a negative 1 at the end, sorry, not 0. Yeah, so this is supposed to be negative 1. There's a negative 1, there's a negative 1. So this is a negative 8, negative this guy, that's 12. Yeah, so we're getting this. The left is equal to the right, but there's no t. So whenever you get the left is equal to the right, meaning these guys actually intersect at many points. That's how we conclude it. Yeah, to say this is going to be true for every value of t that you choose. Yeah, the left is always going to be the right. So they do intersect at many points. Yeah, that's how we write this guy. So if the numbers are totally different, meaning there's no intersection, even if the t has cancelled, right? In the third example, the t, yes, go to cancel, but we are having an outcome of 0, like negative 1 is equal to negative 1, which makes sense. It's true, right? So meaning there are just so many points of t. No wonder we are saying the line is lying directly on the plane. So they are meeting at so much infinite points, so to say. Yeah, so that answers your third one. Then look at this guy here. How do we check if two planes are intersect in space like this here? You're seeing one plane is coming like that, one plane is going the other side. So here is an example. Yeah, so the planes could also be, these are the conditions they give us. So they are saying if two distinct planes intersect, the solution is a set of points that lie on the line of intersection. So this is almost like how we used to check for the description of whether lines are going to intersect in space or not. So when we're given two equations of planes, we have to put them in their original form. This is just going to be the same as 2. Then you say x minus 0. Then you put, just get the coefficients of the x, the letters that you have. So I'm just going to get a 2, a negative 1, and a 1. For this guy here, I'm going to get 1, then 1, and also 1. So that's the first thing that you do. So this is like, these are like normal expressions, right? You remember how we form the equation for the plane? We're using what? The normal and the point 1, like the x0 point. Yeah, so here we're just going to get the normal for the first plane and the normal for the second plane. Then we try to analyze them to see if they are multiples of each other. Yeah, so these guys here are going to be, so these guys are going to be related. You have to check. So we're going to say, imagine we say 2, what? Let's say 2 multiplies t, right? Any letter that you want is equal to 1. Also negative 1 multiplies t is equal to 1. Then 1 t is equal to 1. There is no consistent relationship between these two guys. There is no scalar multiplication that connects the first normal vector to the second normal vector. So meaning these guys here actually intersect. So this is a yes. They intersect because they are not scalar multiples of each other. That's what we are saying. Yeah. So maybe this one that will be different will make sense. So the normal vectors here are what? We're going to pick, let me use blue. We're going to pick the coefficients. The first normal vector is 2, -6, and -7. Then the other guy here, the second normal vector is 3, -9, and a 6. Oh, this has to be this, sorry. This is 4, right? Yeah, so it's 2, -6, and a 4. That's a 4. Then we have 3, -9, and a 6. So we try to relate these. Imagine I say 2n is equal to 3. Then again I say -6n is equal to -9. We can reduce this to be what? 3 there gives us 2 times. Then -3, this is going to give us a 3. You're seeing they look alike. The last one as well, we're going to have 4n is equal to that. Reduce this by 2. That's 2n is equal to 3. So there's a consistent relationship between these guys here, meaning they are parallel because they have a scalar multiplier that is connecting them. Yeah, so these guys are going to be said to be parallel, and if they're parallel, meaning they are distinct, they are not going to intersect. Yeah, so these guys do not intersect, these two planes. Yeah. Then the last one, we do the same. We have n1, which is 1, 1, -1. The next one, we have a 2, 2, and negative this. So for these guys here, you notice that they do not have a scalar multiplication. They do not have a relation as well if you try to connect them, because of the mismatch that you're able to see on the last guy. We have what? N is equal to 4. These others just give us n is equal to 1, n is equal to 2, n is equal to 2. So we have a mismatch, meaning these do not intersect. Yeah. So is it true? Let me say. Oh no, when there's a relation, so here they do intersect, right? Because there's no scalar, they're not parallel. Yeah, so they do intersect. If they are parallel, meaning they don't intersect. If they are not parallel, meaning they're going to meet someone, so meaning they intersect. Yeah. If there's a relation, a scalar multiplier, meaning they're going to be parallel, just like case 2. So yeah, this answers this part. And the last thing that we talk about is on the 5.5, the vector valued function. So this part here explains that if you're given a function, yeah, so let's call it RT, it can be expressed in terms of vectors. So you can talk about the first part, F1 with respect to T as that, F2 to T as J, then you have F3 to T as K. So we have components. Every function in 3D can be related to a particular vector. So we're saying vector valued function, we call them vector valued functions in space. Maybe this guy here will help you. They're saying represent a parabola by a vector valued function. So we can let x be equal to t, then the y is going to be, where there's x, put t, right? That's going to be t squared plus 1, meaning the RT that we're interested in is just going to be ti, because that's x, right? Then we're going to have plus y is the y component is t squared plus 1 and j. This is basically what you get. Someone else will say this is the same as r of t as a vector valued function would be t and t plus 1, like this. Yeah, so you just let the first letter x in this case to be equal to t. That's what we have. Yeah, and when given these functions, since they are functions, we can treat them the same way we treat those functions under calculus, to say these can actually be differentiated. And when you differentiate them, you are going to be getting the derivatives of each part, like the I derivative, the J, the K derivative. So if we say R prime of T, this is going to be F prime of T1. This is I2. This is F2 prime of T, J, then plus F3 prime of T, K. So we partially differentiate all of them. So like, this is just what they try to explain here. Don't mind these guys here. Limits means differentiation, right? Yeah, so look at the first example that we're having here. If we want to get dr dt, the answer here is just going to be differentiate this using product rule, because you have t and you have sine t. So this is your u, that's your v. So when you get your u prime, that's just going to be a 1. Your v prime, that's just going to be cos t. So multiply 1 times sine, that's going to be sine t, plus t times cos t, that's t cos t. This is I. Then plus, when you differentiate this, you get negative 2 sine x. Oh, sine, we're using t, right? Yeah, so we're having t so sine t, then cos t, j. The last one, when you differentiate it, it's going to give you the 2 over 3 comes down. That's going to give us a 2, then t, negative 1 over 3, this whole thing with a k at the end. So this is basically the derivative of this function. We just differentiate it in a normal way. Just differentiate. Yeah, let's hope this is okay. And the next thing we want to talk about is the ability of us to differentiate it and get the arc length. So we're saying if there's a function on a curve, right, and it's differentiable. So if something is differentiable, it simply means it's continuous. It's defined for every letter, for every number t, in this case, because the functions are going to be in terms of t. And if we're able to differentiate it, we can also get the arc length. So this is st, arc length is going to be represented by st. S of t is just the integral between the two particular points they give you, the modulus of rt. This is what we have. Then dt. This is a formula. So let me give you an illustration here. Before we do that, they are telling us that there's what we call a unit tangent vector, which is just this given by this equation here. And the arc length, or rather the derivative of the arc length with respect to t, is the same as the modulus of the original vector valued function. Then the unit tangent vector is also the same as the derivative of the original function with respect to the arc length. So let me show you this guy here, how we show this example here. So they want us to get t, the unit tangent vector, at t is equal to pi over 3, which is a 60, and the arc length from 0 to 4. That's what they want. So I'll solve it from here. So RT is given to be cos t, that's our I, sin t, then we have j, and this is going to be plus your tk. So from here, we're going to have, they want the unit tangent vector, right? That's what they want. So we're going to differentiate this first, because the unit tangent vector, we said, is the same as, the unit tangent vector is the same as the differentiated expression for the vector valued function over its own modulus, right? That's what we want. So we need to do the derivatives first. So the derivative here is just going to be r prime of t is equal, the derivative of course is negative sine t with the I. This is just going to be cos t with the j. This is just going to be a k, because the derivative of t is a 1, right? Then from here we can get the modulus here. So the modulus of r prime of t is just the square root negative sine t squared plus cos t also squared, then plus a 1. This is going to give us sine squared plus cos squared t. These guys will give us a 1. Remember this from your trig, implying that this is going to give us modulus of, the root of 2. So the whole thing that was needed, our vector, our unit tangent vector, this is equal to this guy. So we'll say 1 over root 2 multiplying the negative sine t, comma, the cos t, comma, the 1. So this here is our unit tangent vector, just this, because this is a vector here on top. Yeah, so we put it it's okay to also show it like this: negative sine t with your I, your cos t with your j, plus your k, everything over root 2. Yeah, we can rationalize, just leave it there, it's okay. The next question, they want us to get the what? They want us to get the arc length from 0 to 4. We said the arc length is equal to the integral. Yeah, so they said what? Oh, we needed to finish this, guys, here. So sorry, here we need to finish it because they want this at t is equal to pi over 3, right? They want us to completely finish it off. Yeah, so we have to replace where there is t, this is sine pi over 3, yeah, then plus this is cos pi over 3, this is j, then plus a k. Yeah, so this is just supposed to be, I preferred writing it like this. So negative sine of this guy here. So this is a 60, right? So sine 60 always gives us what from your special angles? That should be what, root 3. Now it's going to carry negative because of the guy outside there. So we have this like that. Then we have cos what? Cos this guy should be half. Then you have a k this side. Yeah, so this is 1 over root 2. J, then plus a k. You can multiply everything throughout. This is just going to be root of 3 over 2 root 2 plus 1 over 2 root 2 j, then plus 1 over root 2 k. We could have rationalized everything. So if you rationalize everything, that's going to be root 6 I. That's going to be root 2 with a 4 j. That's a root 2 over a 2 k. Yeah, so this is our answer. That's your unit tangent vector. Yeah, then from here we can get the arc length. The arc length is just going to be the integral of this is from 4 to 0. Modulus of this, we got what? Modulus of r prime of t. We got a what? We got a root 2, right? This is dt. So this is going to be root of 2 with a t between this guy. So the answer is just going to be 4 root 2. This is units. Yeah. So this is the arc length. Hope this is okay. Then the next thing here is this is just another vector really. We're just saying there's what we call a principal unit vector, which is the unit tangent vector divided by its own modulus. Yeah, that's how we get this. Then there's a last guy here which we call the binomial vector, which is simply the cross product of the unit tangent vector and the principal unit vector. It gives us a binomial vector cross product. Yeah, so there's this part here they're saying find t, n, and m if r of t is equal to this. So this guy here is very straightforward. The first thing that we do is to differentiate this. We have r of t. R of t is going to give us negative a sine t, right? And this is going to give us a cos of t j, and here we're just going to get a b k. So once you get this, we need its modulus. So the modulus of r prime of t is just equal to the square root, square this guy, is a sine squared t, and the other one will be a squared cos t, then the last one will be b squared, right? So the a can be factorized. That's going to be a, because cos and sine squared will give us a 1. This will be b squared. So this is going to give us r of t. So hope this is okay. It gives us this. According to, we can let, according to your working, under Pythagoras theorem, you know, this can just be equated to c, right? We can just say this is c. So just say this. Yeah, this is c. This is equal to a c. So we just say c is equal to root of a squared plus b squared. Yeah. Then you can use this to get the unit tangent vector, because you just want this. This will be the guy we've gotten, which is our c, which is the same as 1 over root of a squared plus b squared, multiplying all these here, or the original one, sorry, is it, or this same guy, yeah, the differentiated one, because it's what, it's tx is equal to r prime of t over modulus of r prime of t. Yeah. So then from there you can manipulate it. Okay, just try this and just show me on WhatsApp. We can do, we'll do it if you fail to do it when we meet in person. Yeah, so this is very easy. The last thing is the same thing you did in first year physics. They're saying if you give r prime to be a position vector, meaning its first derivative is going to be its velocity and the second derivative will be the acceleration. Yeah, so if you differentiate it, the first time, what you get will be the velocity equation. Then the next one, when you differentiate it for the second time, what you get will be the acceleration equation. If you get the modulus of the velocity, you get the speed. When you get the modulus of the acceleration, you get the acceleration. What? Scalar. So that's basically what we have. Yeah, so this is where vectors end from. Yeah, try this as well. So we have 2 questions that I've given you to try. We'll start with them in our next physical session. Thank you so much for your attention.